You are welcome again in ECE 303 from University of Kufa. We are still in transmission lines and specifically two conductor transmission lines. In a previous part, we talked about how we could measure or calculated or determined the reflection in transmission lines. And we said we could do that by calculating many parameters or one of these parameters, and in a previous part we explained how we could measure the reflection coefficient, which is the ratio between the the reflected energy or power or voltage, to the transmitted one. The reflection coefficient or the voltage reflection coefficient is the ratio between the reflected voltage to the traveled one, or the reflected current to the traveled one multiplied by sign minus or minus 1. So in this part we will talk about another parameter which could get a knowledge about the reflection by determined or calculated, and this parameter is called standing wave ratio. If you remember, we said that the voltage across the transmission line at any position Z is represented by the superimposition between the traveled to the reflected, the traveled with the reflected, and same for the current. And according to this process of superimposition between the two components, the wave or the voltage along the transmission line will look like a standing wave, or what we call the stationary wave, resulted from the interface or the superimposition between the two components. So if we measure the ratio or the magnitude of this voltage or current, the total voltage or the total current, or the voltage or the current which resulting from the superimposition process, if we calculate the ratio between the maximum magnitude to the minimum one, we could imagine how much reflection is occurred for this system or this transmission line. So let's explain that. As we said, the voltage now along this transmission line is represented by superimposition of the traveled and the reflected, and here we are using the reflection coefficient to represent the reflected component, and same thing for the current. So now if we need to calculate or to determine the magnitude of this voltage, we need to multiply this component or this term by its conjugate to get the magnitude. So the absolute voltage is equal to the superimposition between the traveled and the reflected multiplied by its conjugate, and we know if we multiply any vector with its conjugate we will get the magnitude of this vector. So here we have traveled voltage, and here we have a conjugate of the traveled voltage. and here we have the reflection coefficient as a magnitude and phase, and here we have the reflection coefficient as a magnitude and phase, and also the phase constant, exponential of the phase constant as a conjugate, where we could note all the imaginary component, it has opposite sign with compared by the ordinary one. So with more analysis for this equation, we will get at the final the voltage or the magnitude of the voltage across the transmission line. Okay, it depends on the reflection coefficient square, or the magnitude of the reflection coefficient. Okay, and this magnitude will be oscillated as a sinusoidal, okay, depending on definitely phase constant, reflection phase between the traveled and the reflected, and definitely our variable z, or the position, the points along the transmission line. So along the transmission line, the magnitude of the voltage or the current, the same thing will be or could be dependent for the current. The magnitude of the voltage across the transmission line will be oscillated as a sinusoidal depending on the position of or on this transmission line, at which point I need to measure this magnitude. And beside that, it depends on the phase between the traveled and reflected components, and the phase constant and the reflection coefficient magnitude. So this is the voltage magnitude and this is the current one. Okay, definitely same thing. This equation is same with compare with this. We just replace z, which represent specific position along the transmission line, with d or minus d. So we considered here at the load we have 0, okay, and start calculated or accounts the position when we directed in the generator direction, when we moved with the generator direction. So we have d, and here at the generator we have d, it's equal L, and at the load we have d is equal 0. Or you could keep this form of the voltage magnitude formula, so you could use this or this, it's same. Okay, if we plot this equation, we will get, as we said, sinusoidal plotting represent the magnitude of the voltage or the magnitude of the current. Okay, and this oscillated occurred because the superimposition between the traveled and the reflection or the reflected components. So here we have, according to that, at a certain position we have maximum magnitude, and other positions the magnitude will be minimum. So if we measure the ratio between the maximum and the minimum, we could specify how much reflection occurred along this transmission line, and same for the current. Okay, so if there is a reflection along this transmission line, okay, the magnitude of the voltage along the transmission line will be oscillated as a sinusoidal. Okay, and if this reflection is very large, that's mean, for example, the reflection coefficient is equal 1, okay, so all the power is reflected, so the difference between the maximum and the minimum will be very big. Okay, and the ratio, it's about infinity, okay, or very big number. And as we said, same for the current. So maximum will occur or will be occurred at a certain positions, and minimum will be occurred in another or in others positions. So here again we have the formula for the magnitude, okay, of the standing wave or stationary wave, or the magnitude of the voltage across or along the transmission line. And we could note this oscillated is repeated, okay, for each half lambda. Here we have 2 multiplied by beta, and beta we know it's 2 pi over lambda. So here we have 4 pi over lambda. So along a lambda, the cycle will repeat itself 2 times. We have 4 pi at each lambda. So one cycle, it could be happened with half lambda. Okay, so the stationary wave repeat itself each half lambda, whereas the traveled voltage and the reflected voltage or currents repeat itself, okay, each 1 lambda. So here we could note maximum, minimum, maximum. So the maximum repeat itself at the half of the lambda, and the minimum repeat itself at the half of the lambda. So the distance between maximum and the next maximum, it's half lambda, and the distance between maximum and minimum, okay, it's quarter of lambda, or lambda over 4. Okay, whereas in case of a traveled or reflected, the wave repeat, and we know that, of course, it's more logical, the wave repeat itself at each lambda. But in stationary wave or standing wave, because it's resulting from superimposition of 2 wave, so it repeats itself each half of lambda for the voltage or for the current. Definitely the phase between the voltage and the current is quarter pi or pi over 4, I think, yeah. So pi over 2, 90 degree. So if voltage is maximum, current is minimum, voltage is minimum, current is maximum. Okay. So if we need to specify the distance, okay, where the voltage is minimum, where the voltage magnitude is minimum, this is wrong, it should be minimum, the voltage magnitude is minimum, okay, if this cosine resulting minus 1, okay, so if this cosine, the resulting of this cosine is minus 1, so the magnitude will be magnitude of the traveled voltage multiplied by 1 plus square of the reflection coefficient minus 2 times magnitude of the reflection one. So this minus will be occurred if this cosine is minus 1, where this is the minimum. The maximum, okay, will be occurred if this cosine is equal 1. Okay, so if this cosine is equal 1, we will get 1 plus reflection coefficient magnitude squared plus 2 multiplied by reflection. Okay, so according to that, let's determine when this cosine will be minus 1 and when this cosine will be plus 1. This cosine, it could be minus 1, okay, if this argument equals odd pi's, okay, that's mean 1 pi, 3 pi, 5 pi, 7 pi, okay, if this argument is equal odd pi, so the voltage will be minimum. Okay, and we could consider this position is position for minimum voltage. So could say D minimum, okay, is occurred when this argument is equal odd pi. That's mean n here, n represent integer number 0, 1, 2, 3, 4 and go on. So when this argument is equal odd pi, that's mean the position is position of minimum voltage. Okay, another side, the maximum, we said the maximum happens or is occurred when cosine, the resulting of the cosine is equal 1, and the cosine produce 1 if its argument is equal even by, that's mean 2n multiplied by pi, maybe in next slide, that means 0, 2 pi, 4 pi, 6 pi, and go on. So at this position, or if we have this argument, that means the position is maximum, or represent maximum position, or position for maximum voltage. Okay, so also if anyone asks, what about the match case, or what about the stationary wave or the standing wave ratio if there is no reflection? So if there is no reflection, that means the reflection coefficient is equal 0, and that means there is no any standing wave or stationary wave. So the magnitude is equal straightforward line, there is no any reflection, and the ratio is equal 0 between the maximum and the minimum. There is no maximum and minimum positions. At all position, the voltage, it has same magnitude. So the standing wave ratio, if we have matched line, that means the characteristic impedance of the transmission line is equal to the load impedance. So that means there is no maximum and minimum, because there is no any standing wave, superimposition standing wave along the transmission line. So the ratio between maximum and minimum is equal 1. So the magnitude of the standing wave ratio is between 1 and infinity, because 1, if we have matching case, that means Z naught is equal to the Z load. So the standing wave is equal 1, standing wave ratio, because V maximum is equal to V minimum, and the maximum value of the standing wave ratio, it could be infinity if we have minimum voltage is equal to 0 and maximum voltage is equal to a certain number. Okay. This is an example. We need to prove the magnitude of the reflection coefficient is equal 1 for transmission line or lossless transmission line connected or terminated by purely reactive load. That means we have a transmission line, lossless transmission line, terminated by purely reactive load, for example capacitor or inductor, and we need to prove the reflection coefficient will be 1. That means all the power or the energy, all the voltage will be reflected. Okay, so theoretically we could do that by calculating the reflection coefficient. Okay, using the formula for the reflection coefficient, which we know, Z load minus Z node, Z load plus Z node, the ratio between these two terms. Okay, Z load, it's purely reactive, okay, load, for example inductance, and by convert this formula of complex number to a magnitude and phase, so the reflection coefficient at the end is equal to minus 1 multiplied by exponential minus j2 theta, phase and magnitude. So this is the reflection coefficient. If we need to calculate its magnitude, we need to multiply this term by its conjugate, so its conjugate will equal positive instead of minus or negative. So I multiply this term by its conjugate and take the square root for the result of the production, we will get 1. The reflection coefficient, magnitude of the reflection coefficient is equal 1. That's it. Okay, so again, if we need to determine or specify the position where the voltage is maximum and the position where the voltage is minimum, we said previous slides, the voltage will be minimum. Again, this is wrong, this should be minimum. The voltage will be minimum if the argument is equal odd by, and the argument will be odd by, okay, by doing this multiplication, 2n plus 1, and n is integer 0, 1, 2, 3, and go on. So according to that, we could consider this position is position for minimum voltage. Another side, the voltage will be maximum if the argument of the cosine is equal to n multiplied by pi. So if the argument of the cosine is equal to n pi, we could consider this position is position for maximum. Okay, and again, the distance between maximum and next minimum is equal to the pi over 4, and the distance between maximum and next maximum, or minimum and next minimum, is equal to the half lambda. So minimum voltage, again, according to this, the minimum voltage will be the magnitude of the trouble multiplied by 1 minus magnitude of the reflection coefficient. Maximum, this is the minimum magnitude. The maximum magnitude will be the troubled magnitude multiplied by 1 plus the magnitude of the reflection coefficient. So the standing wave ratio is the ratio between the maximum magnitude to the minimum magnitude. The maximum magnitude, okay, the minimum magnitude here, as we said, the magnitude of the voltage multiplied by 1 minus magnitude of the reflection coefficient, and the maximum here we have plus. So by take a ratio between maximum and minimum, magnitude of the voltage will be cancelled, and we will get 1 plus reflection coefficient, 1 minus reflection coefficient. Of course, reflection coefficient as a magnitude, and this is sampled by capital S, referring to the standing wave ratio. So minimum S is 1, and this is for matching load or matching case. That means there is no reflection, because the maximum and minimum, okay, both of them are equal. Sorry, maximum and minimum are equal. So that means we have magnitude of the voltage along the transmission line is look like a straight line. There is no any oscillated. Okay, but if the reflection is occurred, okay, S will be larger than 1, and it could be infinity if all power or all voltage is reflected, such as if we have transmission line terminated by open circuit or short circuit. So for short, open, or purely reactive load, as it could be expected as infinity or a very big number. That's it. So now we have, or to yet we have two parameters could be calculated or measured, okay, to give us or to reflect how much reflection occurred along transmission lines or along a certain transmission line. First, reflection coefficient or voltage reflection coefficient, by calculating the ratio between the reflected voltage and trouble voltage, or by calculating or by using the relation between Z load and Z naught. And the values of reflection coefficient is confined between 0 and 1. 0 for matching case, because Z load is equal Z naught, so this formula will result 0, okay, and 1 for maximum reflected, refer to the maximum reflected if we have short circuit, if we have open circuit, or if we have purely reactive load. This is for reflection coefficient. Another parameter we could use it, or we could calculate it to get us, or to get, knowledge about the reflection, how much reflection along the transmission line. This parameter is called the standing wave ratio. And this standing wave ratio, it could be 1 if we have matching case. That's mean Z node is equal to Z load and there is no any reflection. And if S is larger than 1, that's mean there is a reflection. And at maximum reflection, that's mean if all the power or all the voltage is reflected, so we could expect, or we expect the S will be very large number, or for more approximately is infinity. So I think it's good for here. Thank you very much.